Okay, good morning, one and all. So today I'm going to start module 5, so which is about spread spectrum communication system. So basically, in the spread spectrum communication system, the information signal is spreaded, okay, by using a code called pseudo noise code. The bandwidth of the information signal will be much more than the modulated signal. Okay, so basically, by doing like this, we will be able to have more secure communication. So it was originally this spread spectrum communication developed and used in the military communications. Okay, so why it is preferred in military communication is to provide a resistance to jamming. So we call as anti-jam protection, and also it will hide the signal by transmitting it at low power. That makes it difficult for an unintended listener to detect the presence of this signal in noise. Okay, so hence this spectrum signals for digital communication were originally developed and used for military communications. Okay, so in what way this spread spectrum communication is different from the conventional communication system? Okay, the difference is uh, in case of spread spectrum communication, as I said, the information signal will be spreaded. By doing so, that will be spreaded by using a code called pseudo noise code. Since that pseudo noise code is random in nature, okay, uh, so that will make the unintended listener, means at the receiver, for them it becomes noise. Only the fellow who is having this code can receive that signal. Okay, so in that way it provides a secure communication, what we can say. And these spread spectrum signals are providing a reliable communication. So because of that, now other than military communications, it is also used in the civilian applications like digital cellular communications. So you might have heard about CDMA 1, CDMA 2000, 2G, 2.5G standards. Okay, and even WCDMA, right? Wideband code division multiple access, and so on. Then it is used in cordless telephones also, and it was used in inter-office wireless communications. So these are some few applications in general about this spread spectrum communication. Okay, so as I said, the basic parameters of any communication system design are: one is the transmitter power, and another one is the channel bandwidth. Okay, these are the two basic system design parameters, what I can say. One is the transmitter power, second one is the channel bandwidth. Okay, so for any communication system, the goal is, or the objective of the design of any communication system is to utilize these two uh, resources, that is transmitter power and channel bandwidth, as efficiently as possible. Okay, so the goal is to reduce the transmitter power. So that is done by incorporating the channel coding techniques. Okay, with the different coding rates, it is possible to reduce the transmitter power and increase the channel bandwidth. So with that, the performance of the communication system will improve. Okay, so in case of spread spectrum communication, as I already said, means to say what are the characteristics of the spread spectrum signal. So one is, I can say, the bandwidth of the information signal will be much more than the bandwidth of the modulated signal. That is the first characteristics of the spread spectrum signal. Second one is the information bearing signal is spreaded by using a code called pseudo noise code. Okay, as I said, the pseudo noise code is uh, random in nature. Okay, and this spreaded signal appears random to the receivers other than the intended receivers. Okay, that in that way, I can say it provides more secure communication. Okay. Uh, as I said, because of the spread spectrum signals provides reliable communication, it is also finding many applications in the civilian this one. So as I said, these are some examples of the use of spread spectrum communication in the civilian applications, like in digital cellular communications, as I said CDMA1, CDMA 2000, WCDMA, which is used in 3G, and so on. It is used in cordless telephones also. It's used in inter-office wireless communications. Okay. So I said that it is a type of modulation in which the modulated signal bandwidth is much greater than the message signal bandwidth. Okay. And then I said the spreading of the message signal spectrum. Okay. The spreading of the message signal spectrum is done by using a spreading code called the pseudo noise code, right? And that pseudo noise code is independent of the message signal. Okay. So the pictorial representation is shown here, right? So this is the information bearing signal. Okay, so this is the information bearing signal. Having a bandwidth of B, and which is passed through the spreading process. See, another input is the pseudo noise code, okay, pseudo random code, right? And these two will multiply. The output of that will be the spread spectrum signal. So the bandwidth of that will be much, much greater than the bandwidth of the information bearing signal. Okay. Yeah. So next we'll discuss about the model of spread spectrum communication system. So as we are aware, any communication system, the conventional communication system, the main blocks of the communication system are channel encoder and the decoder, and the modulator and the demodulator. Okay, these are the four basic elements of a digital communication system, right? The conventional digital communication system. So in the spread spectrum communication, in addition to these four blocks, channel encoder and decoder, and the modulator and the demodulator, in addition to this, we have two identical pseudo-random sequence generators, one with the modulator at the transmitting end and one at the demodulator at the receiving end. So this is the difference between the spread spectrum communication system and the conventional communication system. In the conventional communication system, we don't have this pseudo noise sequence generator at the transmitter and the receiver. Okay. So here, by having these pseudo noise sequence generator at the modulator and the demodulator, so it is possible to achieve a secure communication and which is more reliable. Okay. Sorry. Here, the major challenge is the time synchronization of the pseudo noise sequence, which is generated at the receiver, right? With the pseudo noise sequence contained in the received signal, right? So that synchronization, why the time synchronization of the pseudo noise sequence, which is generated at the receiver with the pseudo noise sequence contained in the received signal, is required to properly despread the received split spectrum signal. Like in conventional communication system, like we said, coherent communication, right? There, how the phase of the carrier need to be synchronized, okay, to get proper information at the receiver side. In the similar way, here the time synchronization of the pseudo noise code, again the code pseudo noise sequence is very important, and it is a challenge because only the user who is having the pseudo noise code will be able to receive the intended, means the information signal. For them, for others, it will become a noise. Here, then what type of channel encoding techniques are used, and what are the different types of modulation techniques opted for this, right? Uh, and all to say, so depending upon the application, the channel encoding techniques are used. Right? So the type of modulators preferred, the more popular modulation techniques preferred in case of direct sequence per spectrum or phase shift keying, and that is BPSK, and for frequency of spectrum it is FSK. Okay, to say the classification of spread spectrum communication, we can say broadly there are two different types of spread spectrum communication systems. One is direct sequence spread spectrum communication system. Second one is a frequency hop spread spectrum communication system. Okay, so as I said, the type of modulators, okay, preferred are what? BPSK in case of direct sequence spread spectrum system, and in case of frequency hop spread spectrum communication system, the type of modulation preferred is FSK, that is frequency shift keying. Okay, and this pseudo noise codes. Okay, there are a variety of pseudo noise codes. In that, the more popular pseudo noise codes are, one is gold sequence. Okay, gold sequence. Then Edward sequence. Uh, So we'll see those sequence, how to generate and what are its properties and all in the upcoming lectures. Okay. So this is the model of the spread spectrum communication system. Okay. So in general, what I said, the conventional digital communication system will have four basic elements. What are those four basic elements? One is channel encoder, will be at the transmitter side, and channel decoder will be at the receiver side. Then modulator at the transmitter side and demodulator at the receiver side. Okay. So what is special in spread spectrum communication system? In addition to these four uh, basic blocks, it has pseudo noise sequence generator at the transmitter and as well as at the receiver side. Okay, the pseudo noise sequence generator will be used one at the modulator and another one is at the receiver. Okay, the time synchronization of these two pseudo noise sequence signals, means one which is generated at the receiver and one which is there in the received signal, is an important factor, and that is required for proper despreading of the received signal. So, as I said, there are two different types of spread spectrum communication systems, right? So, let us take the first one, that is a direct sequence spread spectrum system. Yeah. So, direct sequence spread spectrum system. So here the information bearing baseband signal is denoted as V of t. Okay, that is the message signal. Okay, is denoted as V of t, which is defined as mathematically. So V of t will be equal to summation n equal to minus infinity a suffix n gt of t minus n into tb. See, this g suffix t of t minus n into tb is a pulse. Okay, gt of t is a pulse, right? Means the information bits are represented either 0, 1, 0, 1 like that, right? So that will be represented by using any of the line coding technique, unipolar, polar, or something. So I represent mathematically like this: gt of t minus n into tb. So this is a shifted version of that, right? And a suffix n is the magnitude of that signal. Okay. So the value of an can be plus or minus 1. Means I have input sequence, right? So which is defined like this. And another signal, as I said, the pseudo noise signal, right? From the pseudo noise sequence generator is also, yeah, just to understand, see, this is my input binary sequence. I have taken here so many ones. I think if I say this is a bit duration, right? So I can say it is 1 and the next bit is 0. I have bit duration is large. Okay, this is my input signal. Okay, binary signal. And next one is the pseudo noise signal. Okay, there is also a binary signal having an amplitude of plus or minus 1. As I said here, it is written. See, the pseudo noise signal from the pseudo noise sequence generator is represented as C of t, which is equal to, again, summation from n equal to minus n to infinity c suffix n p of t minus n into tc. Again, here the value of cn is nothing but the magnitude of that pulse, so which is equal to plus or minus 1. And again, p of t minus n into tc is the pulses, a series of pulses. Right? So these two are multiplied. Okay, the information bearing signal and the pseudo noise code signal are multiplied. That's it. So okay, so output of that, I can, if I denote that as u of t, right? So v of t into c of t is the what modulated signal, I can say. If I am using the carrier, so that is denoted as AC cos 2 pi fct. So with that, I am writing here the u of t is the spread spectrum signal, which is equal to AC v of t c of t into cos 2 pi fct. Okay. And as I said, if I use BPSK, so I denote here that phase by theta of t. Theta of t will be equal to 0, say for symbol 1, and theta of t will be equal to 180 degree for symbol 0, or even vice versa also I can take it. Okay. So as I said, this is my information signal, right? Information signal. And second one is the pseudo noise signal. And the multiplication of these two leads to the spread spectrum signal. Then this spread spectrum signal will be modulated by using a sinusoidal carrier, that is AC cos 2 pi fct, to get the BPSK modulated signal. Okay. So means based on this binary sequence, I will be able to change the phase of the signal. So here, what you can understand is, see, I have taken, see, this is my information bit. I said it is 1. Okay. And next bit is 0. So here my pseudo noise sequence is, I have taken it is 00, 111, 01. Okay. See, the width of the pseudo noise sequence, that bit duration, I call it as T suffix C. That I say it is a chip interval. Okay. And TB is a bit duration. Okay. See, this chip interval is much less than the bit duration, right? So I have taken here the value of n is 8. Okay, means 8 chips I have taken. 8 chips I have taken. What are those chips? That is 00, 111, 01. So this is multiplied with the information signal, right? So if I see here, if I multiply these two, here it is 0, 0, 0, right? So here the magnitude is -1, and here the bit is 1, right? So +1 into -1, it will be -1, right? So I have written two -1s here, right? This is 0, 0. Then here it is 111, right? So that is having a magnitude of +1. So that into here the magnitude is +1. So +1 into +1 is +1. So that is why I have written for 3-bit duration +1. Okay. Next bit is 0. That is having a magnitude of -1. So -1 into +1 will be -1. So that is why it is written -1. Okay. So next bit is what? It is +1, right? That is 1, right? +1 into +1 will be +1. So that is why till this it is +1. So till this is the for 1-bit duration. So till this point, what I can say. Yeah. So till this point, okay. So yeah, I think I can say. See, till this point is one. This one. That 1-bit sequence means the 0. Yeah, bit 1. This is the information bearing signal is multiplied with so many bits of pseudo noise signal. The product signal will be this. Okay, this is for 1-bit duration of the information bearing signal. Like that, again it repeats for another bit. So next information bit is 0. That will be multiplied with this pseudo noise sequence. Again, this pseudo noise sequence repeats. So this is the duration of one cycle of the pseudo noise code. That is 00, 111, 01. So that repeats again. 00, 111, 01. That will be multiplied with the information bearing signal. So after this product signal, which will be fed to the BPSK modulator, means depending upon this spread spectrum signal, right, the phase of the carrier will change. So for 0, I said it is 0 degree, or it may be 180 degree. For 1, it may be 0 or 180 degree, right? This is how the spread spectrum, that direct sequence spread spectrum works. Okay, this is in time domain. Okay, x-axis is time domain and y-axis is amplitude. So to say how does it looks in frequency domain is I hope is it clear about information signal, pseudo noise signal, and product signal.
Yes, sir.
So
It is very simple operation. Just multiplying the information signal, which means the binary sequence with the pseudo noise code, I get the product signal. Then I will be modulating through BPSK. So in frequency domain, as we know, see, multiplication of two signals in time domain, right, will be equal to what in frequency domain? It is the convolution of their Fourier transform in the frequency domain, right?
Yes, sir.
That is what. Yeah, was this waveform. Yeah. So this is what I wanted to say. So this is uh, mm, so uh, this is basically so the message. Uh, sorry, this is the pulse of message signal, spectrum of the pseudo-noise signal. The convolution of these two means uh, that is in time domain. I said it will be multiplication of these two. If I multiply these two, means two rectangular pulses of different width, I will be getting a trapezoidal wave. This is what the spectrum of the. So this is about the demodulation of direct sequence per spectrum signal. So as we are aware in demodulation, so again we use the correlator. Right? See here, R of t is the received signal, received spectrum signal, which is again multiplied with the pseudo-noise code. Right? Then output of that will be multiplied with this gt of t cos 2 pi of ct, then integrated. Means this part is correlator. Second product modulator and the integrator is the correlator. The first step is desplitting process. The R of t is a spreaded signal that will be despreaded by using the same pseudo-noise code, right? So that is the first step. After desplitting, it is applied to the correlator. So after correlator, we know it will be sampled and it is applied to the decoder. For further, it is decoder okay, for further processing of the signal. So this is how the demodulator of demodulation of direct sequence per spectrum happens. So to say a little bit about the direct sequence per spectrum, as I said, the information rate to the encoder is R bits per second. Okay, so the information rate at which I am applying to the channel encoder, I take that as R bits per second. Then the available channel bandwidth, I will be denoting it as W hertz. Okay, so as we all know, bit rate and bit duration are inversely proportional, right? So the reciprocal of the R, which is nothing but the bit duration. So TB will be equal to 1 by R. So that will define the duration of the pulse corresponding to the transmission time of an information bit, right? So the pseudo-noise code is at a rate of W times per second. So W is what I said, it is the channel bandwidth, right? So pseudo-noise code rate will be at that time, at that rate. So the reciprocal of the channel bandwidth, okay, means W is TC. As I said, TC is the chip duration or chip interval. That is the pseudo-noise code interval. That will define the duration of the pseudo-noise pulse. Right? I said it is chip or chip interval. So how these two are related means the channel bandwidth and the bit rate. Okay, so these two are related, and their relation is known as bandwidth expansion factor. So here B suffix E, which is equal to W by R, is the bandwidth expansion factor, I say. So BE is the bandwidth expansion factor, which is equal to W by R. As I said, R is 1 by TB and W is 1 by TC. So if I substitute that here, I can rewrite that as TB by TC. Okay, actually W is 1 by TC and R is 1 by TB, right? So I can write that as TB by TC. Means it is a ratio of bit duration to the chip duration. TB is a bit duration of information bearing signal and TC is the bit duration of the pseudo-noise signal. Okay, and this L suffix E, I can denote it as again TB by TC, and this L suffix E is the number of chips of pseudonoise sequence per information bit. Okay, for information bits, how many pseudonoise sequence will be there. So whatever the example we have considered, in that case, the number of pseudonoise sequences will be 8. Okay, for the example, what I have considered, isn't it? Yeah. So as I said, at the receiver, U of t will be multiplied by C of t. I have taken their R of t, so you can think it is just for sign convention. Okay. So when I multiplied with C of t, right? See, the spread signal with modulation was what? AC, V of t, C of t, cos 2 pi of Ct. When that is multiplied with C of t, I get AC, V of t, C square of t into cos 2 pi of Ct. And since C square of t will be equal to 1, okay, for all values of t, why it is 1? Because it is plus or minus 1. If I square it, it will become 1 only. Right. So I will be getting the signal as AC V of t cos 2 pi of Ct. Okay, at the receiver side. So this AC V of t cos 2 pi of Ct will occupy the bandwidth of say R hertz, and which is the bandwidth of the information bearing signal. So this is how we recover the information bearing signal in the spread spectrum communication system. So with this, I think what I can say, whatever I have planned for today's session is this. So what, just to have a recap, I have discussed about what are the characteristics of the spread spectrum signal, and what are the different types of spread spectrum systems, and what is the model of spread spectrum communication system, right? And in that, I discussed about direct sequence spread spectrum communication system, both modulator and as well as demodulator. So if you have any doubts, you can ask me.
So can you show the previous slide?
Previous slide, this one?
So
yeah. So here I am denoting the information rate, so the incoming message signal to the encoder as R bits per second. Okay, and the channel available bandwidth is what? W hertz. Okay, so we know bit rate and bit duration are inversely proportional. That's why I'm writing TV is equal to 1 by R. So the TB means that the bit duration, right? That will indicate the duration of the information bearing signal. And then I said that the pseudo noise code is at what rate? It is W times per second, means W is the channel bandwidth, I said, right? So the pseudo noise code rate will be at that rate, and the reciprocal of that will give you the chip duration, means the pseudo noise code duration. So hence TC is called the chip interval, and the ratio of this W and R is known as bandwidth expansion factor, so which is equal to W by R. So here this bandwidth expansion factor, usually it will be more than 1, because the W I said is the pseudo noise code rate, right? That will be much greater than the information bearing signal, right? So this ratio means if I substitute W as 1 by TC and R as 1 by TB, so I get TB by TC.